So, welcome to the second Compass Wednesday seminar in this semester. Our speaker today is Brian Mapes of the Department of Atmospheric Sciences here at RSMAS. And he got a PhD in atmospheric sciences in 1992 at the University of Washington in Seattle. And he came to RSMAS in 2004, initially to the Division of Meteorology and Physical Oceanography. And then when we departmentalized and reorganized everything, he joined the Department of Atmospheric Sciences. According to his webpage, he is an expert on atmospheric dynamics and thermodynamics, especially interactions between cloudy convection and larger scale weather patterns. He teaches an undergraduate course in weather analysis and graduate courses in convective and mesoscale meteorology and applied data analysis. He advises graduate students in MPO and ATM. And he suggested to give this talk today, which is entitled Pattern and Meaning in Mesoscales. So please.
All right, thank you, Roland. Let me get started here. Yeah, thank you, Roland. Thank you all for coming back. I miss you all. Yeah, and you know, these are tough times. So you know, you got to think and read and have a little community of like-mindedness, I think, to keep us sane. So thank you for coming out. And in particular, let me acknowledge it up front. You know, there's some, yeah, this is an eccentric title or whatever, and you know, somewhat trying to put a good spin or get something valuable out of you know, the marinating in our own thoughts that we're all doing. You know, I'm sure, and for anybody who's lost someone terrible, and my sympathies, and actually just for the young who haven't built your whole emotional support networks and lives and stuff, is a tough year. So, and I feel it too. So I feel your pain and mine. To be honest, for myself, I've had less pain from this than from the other pandemic here, the pandemic of the mind of our times, the pandemic of lies, willful ignorance, and gaslighting, which you know, has been assisted by machine learning and artificial intelligence and the internet, all these things we thought were good. So I think the only way to top all that, or just, you know, stay sane as we spend our weeks and our months and our years dotting I's and crossing T's in a world that seems not to care, is a sense of humor. You gotta keep your sense of humor. So here's what I meant. Let's just unpack the title kind of word by word. Patterns, you know, patterns are interesting. Patterns are what we live for, and but they're hard to measure. They're hard to turn into numbers. And in the most agnostic way, sometimes we mean just anything other than utter randomness is a pattern. And then it turns out you got to define randomness carefully. Randomness is a big space of you know, it's not as clear as you might think. And then sometimes we mean something more targeted, which I'll show you. Or encourage you to explode the word in your mind, features. It's a machine learning word I'll come back to. And sometimes we mean patterns in time. Sometimes we don't mean in space necessarily, you know, snapshots. A cloud looks like a dragon for a moment, but it doesn't behave like a dragon. So sometimes we mean patterns in time, but sometimes that almost verges into what we mean by meaning, which is that a thing has a lasting existence across time, or an identity, or impacts across time. And that is really about the meaningfulness of even giving it a label, deciding it's a thing. And but then, you know, we also, by meaning, we sometimes mean even more, you know, importance to humans. So pattern and meaning are meant to, you know, point upward, I guess, from, yeah, point upward in your minds. And so what are the meanings of patterns? At one level, you know, we just appreciate them. And that's the view of science as, you know, brain art. Science is an art. It's for the human brains of the experiencers. Sometimes we mean, what science gains us sometimes is conditional prediction. Oh, we've found a law of nature, if this, then that. So, that is a view of science as law discovery. And then, then there's prediction that pays the bills sometimes, temporal prediction. There will be a hurricane next Tuesday, not Monday, not Wednesday. And so that's science as a planning tool. And then, if you really understand a thing, I guess, the meaning of a pattern, then you can gain control of it. And so maybe science is technology's root. But all of these, no matter which one gets you out of bed in the morning or pays your salary, they all hinge on causality, which is really the slippery beating heart of science that has been long. It's easy to lose your eye on that. It's easy to lose sight of that ball in the midst of all the associations that people talk about. So I'm a maximalist for causality, and one of the things I'll be selling today is there's good new tools for being a little more focused on causality. All right, so that's pattern and meaning to me. Scales, sometimes we just mean how big a thing is, but we mean the log of that usually. So there's centimeter scale phenomena and meter scale and kilometer scale phenomena. But sometimes we also mean by scale, we really mean the complexity of a thing or inclusiveness. And that's more in when you use words like systems theory, a system includes a lot and a subsystem is simpler and a super system is more complex. And those range really from the uncuttably small, which is the Greek for the atomic, cannot be cut, or individual or indivisible, to the large, which ultimately, is all encompassing or bounded, and that's simple in its own way too, even though it's vast. And so the scales, range from the unit to the all. And meso really is just Greek for the middle. And so, somewhere between the atom and the all are all the mesoscales. And so they're really defined, it's really defined by what it isn't rather than by what it is. It's defined by what it's between. And every field, especially all these outdoor fields, study with, struggle with the idea of scale. And if you haven't noticed, and most scientists don't, there's a word called supervenience, which worries philosophers of science a lot. And that's about a vertical scale that I'll show you in a minute in a picture. But goals and power and importance are at the top, and fundamentalness lies way at the bottom. And causality is these roots or tendrils from the fundamental to the things we desire. And it's a problem for explanation and control and prediction and everything else. And so the reductionist enterprise falters a little, philosophically at least, on whether it's respectable to discretize things, way above the atomic scale. Is discretization a respectable enterprise, or is it a sloppy shorthand for five-fingered approximators? And so I've been reading in this area and reading other fields and stuff. And one thing word we'll see again, protectorates, is that there's reason to believe that maybe sometimes there's a physical floor above the abyss of causality, going down to quantum noise. And causality, sometimes you can build a floor, and sometimes you can at least build a catwalk across this abyss. So let's see. And all this, by the way, none of this is new at all. And so here, in fact, here's a beautiful, the word emergence is wrapped around all this. And here's a 1939 essay on it. And one ancient weighty utterance is, "There's nothing new under the sun." So, people have been thinking about this for a long time, back before they could do anything about it or measure very much or have very much data to work with. So let's get back to supervenience here. Here's the Wikipedia page on supervenience. And it's about this, it's about there being this whole hierarchy here, that elementary particles make up atoms, which make up molecules and cells and living things and social groups. And the upper levels are supervene on the lower levels. So that means when you're trying to, explain what's really causing things up here. Well, it's that these are really causing it, but actually these are really causing it, and these are really causing it, and this is really causing it, and turns out it's quantum noise down there, and so nothing's causing anything, and you're lost. That's why I call it a crisis. And there's starting to be kind of a mathematical framework. This doesn't worry your grandmother, but it worries certain philosophers of science way out there. So here we go. I've been fond to find that neuroscience is working on this, and there's some people who they work on mathematical rigor on the one hand, but on the other hand, their query is how balls of neurons do things like cognition and decision and action. And so I like this guy Eric Hole here, and how do we get from atoms to agents? And this is maybe my first little tip of an iceberg of reading I've been doing about how information theory can significantly reframe the issue or frame it in the first place in a way. Give it some rigor. So I like this guy Eric Hole. All right, but let's talk about our field. Mesoscales in our field. And fluids in general, there's long been kind of a failure of imagination about mesoscales as expressed in these arts, and because we don't have a sense of any importance to them, because there's no meaning to the meso parts of pattern, we kind of either don't notice it or we don't know how to, who knows, but you don't know what to do with it, right? Fond of this book, just recently finished, the Overstory. You can't see what you don't understand, but what you think you already understand, you'll fail to notice. So there's this slender window called learning between stuff that you don't notice anymore and stuff anyway. So here's Da Vinci wrestling with how to draw fluid flow, and you can tell all his eddies are really just the size of the pipe. Initially, some of his later stuff he got better. So he was observant. He didn't like this, and he was observant, and he got better. And I also love this painting. It came out in BAMS. It was fished out of a basement in BAMS, 10 years ago, and published in BAMS a few years ago, and it's on the Mesos website. And it was a guy was commissioned, a meteorologist with an interest in art was commissioned to paint what he thought a satellite would see when someday we can afford to launch a satellite. And this was it. There's a synoptic scale, and you see the Norwegian cyclone models in the front, cyclones with fronts. And there are little cloud streets of cumulus clouds. And if you look super close, there's a little hurricane over here in the Caribbean, although it's vastly undersized, I think. And only way up here, where the mountains have mesoscales, are there any mesoscale clouds? And the guy just got tired of trying to add mesoscales and just gave up. So, it's all synoptic and convective. And I didn't pay much attention to where I got this from. But of course, the ocean's first, blurry views dominated the ocean as well, I suppose. And today what you can do is type zoom.earth. If you haven't noticed this, type zoom.earth into a browser. Boom, the world today is on your screen. And, every 10 minutes, you can make loops every 10 minutes, frames every 10 minutes. So there's a random day last week of the Atlantic Ocean. I guess I didn't capture any land. And here's what the Atlantic is full of on a random day, shallow clouds. And okay, so here's the thing we care about, because the average albedo of all this is crucial to the Earth's climate. But actually, the albedo locally plays almost no role in what's making the pattern. So there's all this patterning. It's important in its average, and yet it doesn't feed back much on itself. So how could we ever achieve, this is the supervenience crisis here, right? How are we ever going to get a robust confidence in the average value of the climate that we care about? Because when we have to just, I don't know, how do we deal with these mesoscales? We can assume they're random and just average them away, just blur our eyes and put up a blurrier camera and measure its photons, and that's it. But But maybe there's information in this pattern. There's certainly a lot of information in this pattern that we as observers appreciate and enjoy. Man, how informative. Maybe that information can become valuable if we do something other to it than just, pay a lot to resolve it and then average it all away again. But, what would it mean? What would it, philosophically, right? Superveniently, what would it mean to say that we're getting the average right for the right reasons, as opposed to last year when we got it right only, by averaging. So, what do you do with all this pattern, what do you do with all this pattern mentally, philosophically? All right, so in deep convective clouds is the same day. Just slid the window over, zoomed on Earth. Anyway, it's great. And so here, in the infrared, you see the high clouds and the deep clouds, and these blobby bits are deep convection. And that too is a big part of climate, and that is also precipitating convection is also locally important. In other words, there's a strong job or role for precipitation in the dynamics that make the pattern itself. So now we have a pattern that's interacting with the importance variable that we care about. And so maybe if we understand the role played locally by this stuff we care about, we'll gain some confidence that it's larger scale statistics. We have those right for the right reasons, because now it's playing a role in its own dynamics. But what would be this strong job or role for mesoscale patterns in deep convection? Does understanding that role lend us greater confidence? Tell us the right answer or something? Evidently not, I would say, because here's one of the world's first convection permitting global models. And if you tune the boundary layer scheme up and down, this stuff can do the job of deep convection, and this stuff can do the job of deep convection, and they both do the job. So doing the job doesn't tell you, which one you're going to get, tragically. And this, by now there's a whole family of these global storm resolving models, they like to call them now. Bjorn Stevens coined the term, borrowing from Tim Palmer, the Palmer-Turing test. Can you spot which of these is a satellite image and which among these is a satellite image? And you'll notice this was from an initialized model exercise. So you see, the same front is over Western Australia in all of them, and this same cyclone in the Central Pacific is there in all of them. The synoptic structure is the same, because this is just a few days after an initialization. So the synoptic structure is the same. So how are we going to tell which one's real and which one is fake? And the answer is all in the texture. It's all in the mesoscale texture. And easy to see that there are differences. I don't know, what's the most stark contrast? I don't know, some are more spider webby and some are more, this one's more spotty and blobby. That looks fake to me. Anyway, somehow the mesoscales have the information. And I'll tell you, it would be so easy to train a machine learning job to, give it a few hundred labeled examples, and it would be no problem for that thing to learn to tell you which model any given snapshot came from. That's an easy problem. But you give it to a person, well, what would we do? Would we have to go through words? Would we have to just try to describe that this one's filmy and this one's spotty, and then we'd see a new one and we'd say, well, is that filmy or spotty? What would we do? It's unclear, I guess, whether humans could learn that as well as could a machine learning. So it's an interesting, instance, I guess, of all this. The oceans have their mesoscales too, and their sub-mesoscales. Here's just a naming difference. Maybe I hope I have this right. I hope I'm using the terms right. But again, here's the climate problem drives it. So we have this averaging problem. We want the average. And so we're going to get a better average if we resolve more and more details and then average them away. Maybe seems to be that's somewhat the driving thing of this. And this was one of the many job ads in the inbox anymore. This is for a PhD student. investigate the effects of the newly resolved small scales here on the energy flux on the large scales, on the basin scale, and so on. So this little red box here is this, and this black box is this with its little red box in it. So impressive, right? Impressive computation. We got all this pattern. What are you going to do with all that pattern? I guess average it up in some way. And I never quite understood the ocean words meso and submeso, but fishing around the other day, I found that the mesoscale revolution was called synoptic vortices in Russian literature. So that would be more like the atmosphere, that these geostrophically balanced things might be called synoptic, and then submeso might be kind of what we mean by meso. Everything bigger than the mixed layer depth turned sideways, and below that is microscales. Anyway, I'm just learning. I'm not really an oceanographer. I just play one on TV, and I'm and as an MPO director, I should know. All right, and we also learned here's a speaker just the other few weeks ago who I screen captured, whose slide I screen captured, and that is that the mesoscales sometimes maybe actually interact. They aren't just, so you can't just average them away. In other words, they're interacting. In a nonlinear way. So for instance, if you blow a smooth wind on the ocean, you get only this much turbulence. If you blow a time variable wind, you get this much. And by the way, that's an exponential scale there. And you can imagine just, an instability depends on the, wave breaking depends on all the scales that make the wave tip over. So, so the scales really do interact. And in that way, including them is not just, it's not just some pretty details that then you average away like in the clouds. This maybe this is genuinely interactive. And other fields have these kinds of things too. I get this from Sam Perkis, but self-organization of shellfish beds. So all the sciences wrestle with this problem of patterns and what to make of them. So that was a kind of extended introduction, but to the whole idea realm here. And let me get a little bit more specific now, just about, I guess we're still unpacking the title, mesoscales. And there's, mesoscales are between some tiny scale and some completeness scale. So let's talk about mesoscales. Maybe there's like 3 tiers. There's the ones just barely above the foundation of atomic, uncuttable fundamentals. And that is that you got to just kind of rediscretize at the next scale up from the floor. And then there's, and then above that is the mesoscales, deep in the mess, far above the floor, far below the ceiling. And that's where there's a lot of play for the newly discretized entities you've defined to interact and play. And then there's, I guess you'd say mesoscales near the whole, regional climate or something, starting to feel the domain limit, but not a closed system. And I guess we don't call that meso anymore. We just call that large scales, and you just gotta tackle it. There's 7 seas and 7 continents, and that's the scale of the human interest anyway. So these we would just call large scales. So really, I'm just going to walk you through these two. How do we get above the fundamental, and then what do we do deep in the mess of mesoscales? And then at the end, I'll bring it back, and we'll look at other fields, other sciences and stuff for some examples here. And I'll try to bring it back at the end to the atmosphere-specific examples, especially those shallow convection where there's so much pattern. And what can we do about it? And I'm going to make the pitch that informatics, or the study of information, which is a real physical quantity. It's the negative of entropy, and there's a bunch of tools there that we can use for causality inference, for machine learning, which is kind of like a technology that can be put to use for pure science, although it is also put to use for, pandemics of lies and willful ignorance. And then hopefully some of this can be a meso community gathering glue for us as well. And I've set up a listserv that I have not yet populated, but I'm selling you on it today as part of my reason for this seminar. So, all right, I'm just rolling on. I don't see any hand. I don't see people's faces. I don't see hands. So I'm just talking to my screen here. So speak up if you need to, or pop up a chat or anything if you need to. I think that would come up. All right, so let's start mesoscale patterns near the base, near the fundaments, the foundations, the basements. The atomic scales, uncuttable, the discrete cells. This is a word from walled enclosure, can be treated as one thing. And individuals, as we do in living things. And so atoms and molecules, how do those become nanotech in biology? Man, there's quadrillion dollars have been spent on this, as you might imagine, and a lot of powerful minds have spent their lives on this. Biology itself then has its cellular scale, its organ scale, and its organism scale. Kind of these, you get a sense of these discrete steps that life has learned to do, for its purposes. And then social sciences, we have the individuals and groups and communities and on up to, humanity. So down at the near the base here, in physics, here's a famous manifesto from 1972. And it's called More is Different, period. And this was, Physics Today had a recent story about this, about how, why was a manifesto necessary? Of course, more is different. And yet, earning the respect, I guess this was the generation, 72, right? So the great grandfathers who had, decoded the atom and the quantum and stuff were still around, and they owned physics, and physics was the great successful dig to the bottom of causality and of supervenience. And, along came people who are studying, things in the real world and had to try to justify themselves. And so here was his manifesto, More is Different. The reductionist hypothesis may still be a topic for controversy among philosophers, but among the great majority of active scientists, I think it is accepted without question. As of 1972. The workings of our minds and bodies and of all the animate and inanimate matter of which we have any detailed knowledge are assumed to be controlled by the same set of fundamental laws, except under certain extreme conditions. We feel we know those pretty well. So this is the supervenience maximalism. All right, the main fallacy in this kind of thinking is that the reductionist hypothesis does not, by any means, imply a constructionist one. The ability to reduce everything to simple fundamental laws does not imply the ability to start from those laws and reconstruct. Duh. Again, my grandmother wouldn't need to be told that. But physicists do. The constructionist hypothesis breaks down when confronted by the twin difficulties of scale and complexity. So that makes them, anyway, I think of them as one thing in a way. The behavior of large and complex aggregates of elementary particles, it turns out, is not to be understood in terms of a simple extrapolation of the properties of a few particles. Instead, at each level of complexity, entirely new properties appear, and the understanding of the new behaviors requires research, which I think is as fundamental in its nature as any other. So this is kind of defensiveness about, are we fundamental or are we just applied, are we all just applied science as looked down upon by some? All right, and so 30 years later comes along this lovely article, Enjoyed the Middle Way. I love these little punchy three-line titles. And this used the word mesoscopic. So in physics, the mesoscopic is the word for this stuff. And mesoscopic organization is examined. And again, the idea is that as yet undiscovered organizing principles might be at work at the mesoscopic scale, intermediate between atomic and macroscopic dimensions. And, struggling to overcome prejudices, conflicts of principle, life in the desert. You get the feeling of that 30 years later, they still felt they were in the desert, conflicting over principles and struggling with prejudice. There's another nice one, the theory of everything. I guess that's a foreword, but boom, right? Boom. And that is this guy Laughlin. So I bought his book, and this is a nice little book. It's a light little physics book. I quite enjoyed it. So A Different Universe. This is that same different. A whole, it's a worldview about, the crowded world instead of the vacuum with an elementary particle in it. And so I enjoyed that book. And he learned that his Nobel was for the fractional quantum Hall effect, where he discovered a thing that it appears that there's a particle that has a fraction of an electron's charge. How can that be? On 1/3 or 1/2 or something. And it's replicable. So, what is that? So he explained it. But a key concept in his worldview here is the word protectorates. So he says mesoscopic physics needs to identify protectorates. What's a protectorate? That's some kind of medieval sounding word. What he means is, it's like a regime, I guess. It is a bounded set of behaviors which is protected from the level below. So quantum noise can't, bust up your DNA, or life couldn't have built itself. So protectorates are a way of being reliable on mesoscales, even though the scale it rests upon is fickle or noisy or whatever. So biomolecules have learned to exploit this reliability. Nanotech's whole job is to try to, build smaller and smaller devices that, don't quit working every time a cosmic ray comes through. And it also had some enjoyable things, the irony of Einstein's life, starting from demolishing the idea of ether, that the speed of light's the same everywhere because there's no ether, and then discovering at the end that, hey, vacuum is not empty. So, and then the warning about nanobobbles, getting too in love with pattern for pattern's sake, I guess. All right, so maybe the super powerful paradigm there is, there's one page called quasi-particle, but if you go to collective excitations, it redirects to quasi-particles. So quasi-particles and collective excitations are emergent phenomena that occur when a complicated system behaves as if it were a vacuum with particles, but the particles are different than real particles. They're like the fractional charge of an electron or something. And so that is, it's just a whole new way of thinking, which is why it's a different universe in that mindset. And you might say this is all getting pretty far afield, but there is a fluid dynamics analogy I enjoy, which is on a vibrating liquid, a drop can bounce on its own wave forever. And furthermore, you can steer the drop with the vibration of the bed of water. So here's a big wide bed of water, and yet a localized phenomenon can exist that is it's as much a wave phenomenon as it is a particle phenomenon, and that's a fun YouTube to watch. Okay, so it seems like a special thing or a curiosity, but because it survives for a long time, maybe it's more relevant than it sounds. In other words, it is a protectorate. This regime of behavior is a protectorate. And although it's hard to start it, maybe you have to, maybe it's hard to start it, but, it endures. And so in the end, we observe what it endures. And then, of course, the protectorate of genes is, the life has managed to make sense for 1 billion years because endurance endures, and robust persistence is what you gain from a protectorate. And substrate independence is the other thing you get, which is where artificial intelligence may be smarter than me one of these days. All right, so discretization, the whole point is this: if you have a protectorate, that'd be a good reason. If you don't, you still got to discretize, right? And to talk about mesoscale, you got to draw a line, you got to have a floor. So one thing you can do that's just arbitrary is data. We got time series every so often, or we got pixels at some resolution, or voxels in 3 dimensions. And, you can just, from that, you can just build the numerics of PDEs, the sort of stuff Mo does for a living, and that gains you computing. Maybe, to heck with the patterns, they'll emerge and they'll do what they do, and we don't have to think about them, right? We just make as fine a grid as we can, calculate the answer, and trust it more if we make a finer grid. Maybe. Okay, and then there's also so you can do science that way. We can say that patterns are just not worth patterns are not science. But the next thing is, we can use patterns at least as a diagnostic language. So we can speak of objects. that in this ordered space, we can have things that touch and things that don't touch, contacts and gaps, and we can, contiguity is the word there, and we can take contiguous things and call them objects, and then we can subtly call them systems, like mesoscale convective systems, and then we can measure their size and their length, and we can do these morphometrics, and we just categorize the world, and there is a huge cottage industry of mesoscale convective systems. Just count the blobs and say how many there's more on Thursdays, and the long ones are less rare than the short ones, and whatever. There's just, as soon as you give a definition, man, an army of people goes and just does all you can do with a definition. So there's that. And then of course there's modes where we project our fields onto a basis set of patterns like Fourier things, and then spectral peaks, which are objects, get a name, that is the Madden-Julian oscillation and so on. But if you want to get beyond that, either kind of modes or objects, I want to again remind you that this word features is up and coming. So what's a feature? Here's Wikipedia on feature engineering. It is the process of using domain knowledge, like of the atmosphere or ocean, to extract features from raw data somehow. And it's called mining, I guess. All right, and a feature is any attribute or property shared by all of the independent units on which analysis or prediction to be done. Any attribute could be a feature as long as it is useful. So in other words, patterns can be features. So this word feature is very general. It is something about that. And it can be objects, and it can be patterns, and anything. So feature is a big word for us. Features. All right. So that was our So you up from the bottom, you discretize somewhere by hook or by crook, by the finest grid you can afford because of computers, or maybe there's a protectorate, and you're really talking about things that make sense to talk about. Clouds, and they have a finite size. And if you had half a cloud, it wouldn't work anymore. Or something. So maybe there are real protectorates. We don't quite know in general, but okay. So we've done it. We've discretized. We've drawn a line above the abyss of supervenience. Now what can we do? And the next thing I think that that I never was taught, never learned about, that you can do with discrete objects is to use the language of networks. And networks map directly to matrices, so there's math and computation to be done. There's a rigor there. And on the other hand, they are, a visual thing. So they connect our visual sense directly to a computable framework. So networks are powerful, and lots of fields are running away with network. Networks are the math, computation is here, and they get results and meaning out of it. And nobody ever taught me about networks. So they can be merely descriptive or diagnostic, but they can also be a tool in a tool chain that gets to things like, robust causality inference, which is science. So I'm excited about networks in a way, or anyway, you should be, or we should teach it somehow, somewhere in fluid dynamics. But it always involves discrete things. And the language of network theory is graph theory, which is visual. It's for our eyes, but it's also a branch of mathematics. So that is the power connection there. And for causality, there's a subset called directed acyclic graphs. Causality has a direction, and a thing can't cause itself. And there are kind of null hypotheses like random graphs that the famous Erdős, I probably missed some punctuation there. If, as is usually the case, networks are sparse and the connections are linear, that connects to sparse matrices for which there are solver technologies. And so you can draw networks with your hands, and then they're satisfying your eyes, and they plug right into computation. So this is sweeping the world, and physicists are smart. So here you go, physics reports, nestedness in complex networks. So what should we do with this tool? Well, ecological and socioeconomic networks differ significantly from that of random networks. So, physics report is busy talking about ecology and socioeconomic and probably finance because they pay the bill. But hey, come on, let's here, we're a physical science. Why don't we come up with some paradigms or that could benefit from this as well? All right, so network science, if you go to Wikipedia, it is not only a page, it is a whole, what do they call that anyway? There's a whole like chapter, I guess, or many, many aspects of this. It's highly developed and you wouldn't know it exists if all you went to was our seminars and things. So in reading about it, I've quite enjoyed psychodynamics. There's a pretty burgeoning field of psychodynamics, which is something we all have a little intuition about. It's on one hand, it's as fuzzy and ungraspable as fluid blobs. So they have to wrestle with the fuzziness of things. And on the other hand, the examples we all have a little intuition around, and so that's powerful. So this is just to show you. There's something called ocean. It's kind of fun. The 5-dimensional subspace of personalities is openness, conscientiousness, extroversion, agreeableness, and neuroticism. And you discover there's a 5D subspace by looking at all the connections between 20 or 30 questions on a questionnaire. And so network theory has categorized people interestingly in a 5D space called ocean. Science itself actually can be studied with network science. And interestingly, science is topologically a ring. Science has a hole in the middle, for better or worse. And maybe by science, I suppose we mean STEM. Do we mean STEM? I always thought STEM didn't make very much sense. And it's right. If you look at all of STEM and you do a kind of a literature and citation clumping and connections network mapping exercise, you discover that, mathematics is kind of well connected to the physical sciences, a little bit also to the fluid sciences. And those kind of connect to engineering, which is worldly important. So that's connected to kind of brains and business and psychology and psychiatry. And those are connected, of course, to biology and, all this stuff. And biology is connected in some way down to physical, chemistry. Right, chemistry and biology are sort of connected, and chemistry is rooted in physics. And this gap here is really where we sit, a lot of us, ecology, plant sciences, earth sciences, sit in this gap. We fill this gap. And anyway, so network theory teaches you something maybe you hadn't thought of, that STEM is not one thing, not a blob called one thing. It's a donut with a hole in the middle. And I didn't like the word vitality here. So this, the color here is vitality. And brown is very vital, and white is average or less vitality. And we don't have much vitality. And what do they mean by vitality? It's a measure of the speed at which a group of researchers reaches consensus. So I don't think of that as vitality. I think of that as over-patrolled or something, but I digress. All right, so networks. We can talk about networks. We have discrete entities. We can talk about networks, and some of the best analogies are really ecology and competition, or economics, many player games are not zero sum like few player games. So the idea is there's an opportunity. And into that opportunity rush all possible structures or strategies. Really is the unit of competition in this game theory that we'll see in a minute. And and individuals and groups can now be kind of pitted. Individuals and groups of individuals can jointly compete now in game theory. So there's a renaissance in game theory that I feel like might be an opening for us. Mathematical ecology is always interesting, especially for convection is so not unlike forests. So, fields of convective clouds are so not unlike ecosystems in a way. And so the concept of, say, succession after a scrubbing, where little things give rise to bigger things that make room for some mature thing. It's a little bit like what happens to convection after you, it's a little bit like what happens to convection if clouds are everywhere and the big ones eat the little ones, and eventually you end up with this ecosystem of many scales. So here we go. So complexity has many tools that we could probably pick and choose from. Cellular evolutionary algorithms with coalitions, self-organizing maps. I do see that in our field quite a bit. People pick up self-organizing map. There must be a software package so people just do that. And here's the Renaissance in evolutionary game theory, 2018, and collective agency. There's room now for collective agency, so we can really speak of multi-tiered or hierarchical games. It's important. So back to, and to some degree, this language has crept into our field because it is the right way to think. And one example in the climate realm, I guess, and again, back to typhoons versus popcorn, is trying to, here's a smart people there at GFDL trying to understand some counterintuitive dependencies of tropical cyclone frequency on parameters. Whenever you see counterintuitive, that is fun because somebody had an idea and it's not working. It's, an idea is just not pulling, it's not working anymore. And you need a new idea, a bigger idea, a whole nother realm of explanation. So I've enjoyed this, and the visual nutshell of it, as we saw, either of these kinds of worlds, the deep convection of either pattern can do the job. And more generally, they both exist in the world. We saw some blobs like this in the satellite picture I showed you, and we all know these exist. And in a way, they're competing. And climate change may tilt the playing field, either more toward these, God help us, or more toward these, and maybe that'd be nice. We'll get rain more often, droughts less often, and terrible storms less often. So, that's a whole new way of thinking about what climate is. It's tilting the playing field in a game theoretic competition among entities of different scope, I guess. And a weather, example of mesoscale roles is to view the mesoscale patterns role is as a gatekeeper. In a cascade, mesoscales can protect or fail to predict predictability. So if you start with small scales and the large scales are growing at the expense of the small scales, maybe that information has to pass through the mesoscales. And I was surprised to discover an example from the ocean here, which is that ocean forecasting of mesoscale features, by which they mean synoptic, can deteriorate by increasing model resolution towards the submesoscale. So maybe the mesoscales really are a gatekeeper, and if you just the information has to flow through them. So if you forbid them, then error, forecast error can't come up from the small scales because it would have to go through the mesoscales. That totally is unintuitive to me, but anyway, interesting. Maybe in the atmosphere, the role of mesoscales in predictability is a little more as a source of possibly big noise. There's little noise everywhere, but big noise can spoil your forecast. So here's a study from Parsons and Rodwell had an earlier one. The role of mesoscale convective systems in forecast busts. And the idea is that something about these, so here are scenes in which forecasts were surprisingly low in skill. And you look upstream, well, how come that forecast was so wrong? And the answer is something about this evolution was highly unpredictable, yet big enough to make a big impact. So here's some looky here's, but maybe we wish we don't know how to measure what features of these scenes there are. But the title then ends up with mesoscale convective systems. It's the only word we have for a possibly highly diverse range of things, the features, mesoscale features that we wish we had finer handle on. And now I'm going to talk about near the whole mesoscales. So, all right, meso patterns. We wish we had a better handle on them, right? If we just take blobs and call them systems, and then your title is Mesoscale Convective Systems, but it's blurry. So we wish we had better handles on pattern so that we could see whether it's important. We could see if pattern is correlated with importance. We know what our importance variables are, but we don't know what our pattern variables are. And the ones that are easy to compute are hokey. So maybe we need some kind of way in which we can better get a handle on patterns. And a key tool in that, again, under taught in our whole field, I'm trying to introduce it into my class a little more, is information. And information is not just a vague word. Information is a mathematical quantity. It is the expectation value of minus the log of probability. And since 1948, Shannon, we've had this definition, and its units are bits. And by now, everybody knows what a bit is because you pay a monthly bill for how many megabytes you're paying. So bits are very real, and information is as real as it's so real you can charge for it. So it's as real as energy and stuff like that. And from an information perspective, you can rethink convection from an information perspective. Convection processes information, or in other words, it computes. And trouble is, what about the input-output? But so here's an interesting paper, A Brief History of Liquid Computers. And it is possible to make a computer purely from a liquid. And so convection is computation. But trouble is, if you can't initialize it, if you can't give it special initial conditions, what it computes is the output of the input of the output of the input of the output of a chaotic process. But so far we're only using it. Humanity is only using it as a fundamental resource called randomness. So they literally have a wall of lava lamps that they use in their compression algorithms. And it is, an uncrackable code is to encrypt things using lava lamps. No fiendish competitor can guess your decryption. So, yeah. But a little more practically, information can become the scalar that we use to rule our data analyses. There's always one scalar. There's always a scalar. Sometimes people hide their scalar, but there's always one, right? Every objective analysis, where objective means objective, also has an objective, and that is an objective function. And it is, and the reason it always has to be one thing and only a scalar is that only on the number line do we have a measure of the distance between things. And the sign of that distance or difference is better versus worth. So you always got to boil it down to one number to call a thing better or worse than another. And information can become, can be used as that scalar to rule it all. And so sometimes that is called an objective function, and you want to maximize it, or a figure of merit. I like the old timiness. What is your figure of merit in this curve fitting? And negatively, you could call it a penalty function or a cost function. So many words for this, but in the end, information can be our scalar. Oh boy, time. All right. So let me just show you a couple examples of this kind of new informatics grabs at mesoscale patterns. Actually, mostly just one. Deep convection is so crude, I'm not going to even bother it. Shallow convection, we saw, look how rich the patterns are. Let's grab them. And, the first study of this came out of Germany here, and it was sugar, flour, fish, or gravel. And this just, impressions, right? Bjorn Stevens looked at a lot of pictures and said, sometimes it looks like flowers. Sometimes it looks like gravel. Sometimes it looks like fish skeletons. And sometimes it looks like sugar. I don't know exactly what aspect of this is being pointed at. And so humans go in and they label every region on a scene, is that if you had gun to your head, which of those four things is it like? And 135 people did this 14,000 times, all that time spent. And then all that goes into the hopper of a machine learning, which is called supervised because the inputs are labeled, and they're labeled by humans. And so we label our instances, and the machine learns to replace the human. So here you go, sugar, fish, flour, and gravel. So here's, here are the sugar, fish, flour, and gravel regions. And, as the machine learns to do them. And there's a lot of gaps, right? There's a lot of places that you can't fit a label. So this is a gappy thing, and it was supervised because people did it first. And then, so the machine just learns to replace the humans. You do a ton of work with humans, and then you replace them. The disposable human version of informatics. But once you have that, then you can, then you can go on and look at climate variability and stuff like that. Then there's this is an unsupervised example by Leif Denby. Remember right before the pandemic, he was teaching in my class, and we had a whole exercise. We're going to replicate this in my class, and then the pandemic hit, and it's all on the shelf. But this is an unsupervised thing. So instead of having people decide whether it's fish or flowers, you just hurl in a bunch of data, and you say, show me things that are similar and different from other things which are similar to themselves. So, and then you decide how many of those you want. So he did here, A through L. And these are similar, and they're different from that, which are similar, and they're different from that, which are similar, and they're different from these, which are similar. And, you just maximize the contrast, if you like, between things. And I would say it's oversold a bit to say that we've discovered the importance of them. But we have certainly separated patterns, right? We got a pattern categorizer. And in this case, instead of having gaps between places where it fits perfectly, you have like uncertainties. Well, here where it's some lurid color, it is 47% category K and 23% category F and so on. So everything's categorized, but it's categorized non-uniquely. And then as far as giving it an interpretation, is one of these flowers? Maybe this kind of yellowish pattern is flowers, but I don't know. The whole point is now humans have to interpret the category rather than the scene. And there's a big group in Chicago working on this, just AGU so far. But I like that when you sit down to this, you can really go from principles, scientific principles, to a workflow that gives you an answer. And the principles are, we want it to be physically reasonable. We want it to be scientifically relevant, well, whatever that means. We want to be cohesive and separated, cohesive within each class, but separated between them. And stable, meaning it's similar when different things. All these words need to be defined, but you can work from like the principles of what you would mean by a good handle on pattern. So all this is a way we can begin to get a handle on pattern, and not all of us are having to learn this, mid-career or whatever, but not from some class where it's all down pat. So my sales pitch now is let's try to learn this more together with a reading group, or let's call it a thinking group, ideally, together, where we look at the diverse methodologies that people are hurling at this problem, that machine learning and AI methodologies. What's the input? What's the output? What's the objective function that's driving it all? Stuff like that. You can always boil it down to that kind of, who's kicking whom story about it. Even though there's a lot of complications, every method is complicated, but there's always an input, and there's always an output, and there's always a reason that the architecture is what it is. And maybe we can read a bunch of these and kind of figure out what's the, the thing they all share, the list of attributes that tells you what it's good for. And maybe each one, I'd like to make it a goal that every method we look at, our little discussion culminates in a proposable application idea. So we read 10 papers, we're going to have 10 proposable ideas. That's a treasure. So watch your notice for a joining email, and you'll reply, and maybe I'll make you volunteer in order to reply and get on the list. We'll see. But figure out how that works. But there you go. So just to kind of wrapping up now, informatics is so much the future. Just last week, these all came to my email inbox, and it is postdocs at a new AI institute for meteorological applications, and it's a postdoc in machine learning for climate, and it's a new journal, environmental data science, and Florida's UF has got 2 tenure track positions in geography for AI and atmospheric and climate science. Anyway, it's just exploding everywhere, our students we got to get our students trained up, or we're dinosaurs. So, of course, we have to focus on the interpretable parts. There's so many kinds of machine learning, and, many of them are just used to, spread lies and willful ignorance. But the ones that are useful are, thoughtful. They are about process understanding. They are transparent. And so we're going to try and focus in on reading those parts. I am fond of causality, so I'd like to learn, here's Eric Hole again in this, and causal discovery in the geosciences. Boom, right? We'd like to know how that's done. And here's one that had Shangping Shi on it. So, an AI found that Shangping Shi's name was on a paper that might interest me, and that is direct versus indirect. Anyway, that's so deep in the information theory business. And some of our applications, of course, here's viewing forced climate patterns through an AI lens. That's a beautiful paper. Well, this Elizabeth Barnes at CSU is just great in this area, and she's just, teaching us all. We could read her papers, and it's a huge education right there. And then some people are doing forecasting. And so here's, forecasting 500 millibar geopotential height maps. Just jump over all the physics and say, can I train data from the present tells me about the future? Just jump over all the physics. And there's a lot of work by Chris Bretherton at Vulcan Center here of parameterization, using AI machine learning as the parameterization. So here it is, expensive distractions or opportunities. Well, some of both. For observations, resolution is so costly, but it feels informative. Then it doesn't turn into numbers that go into formal science. So, we need to get a handle on pattern so that this high resolution texture that feels so informative can go into the numbers that become workflows that become meaning. So that humans don't become, don't start to wonder what we're good for. And then, of course, we need to understand the roles of these patterns. Do they link? Are they like cascades? Do they just contribute? Do they compete? How to think about it. And, simulation and prediction, in the same way that resolution is costly, building a high-res camera, so is building a high-res a model and running it. And, we got to ask ourselves, for what? Just to average it away again? And so there you go. All right, this is my conclusion, really, just mesoscale patterns and features, new word, between indivisible fundamentals and constrained wholes can be important. For instance, they can exert causality in their own right. And mesoscale patterns and features do not exert causality or have importance. So we have to learn to tell the difference, between a bauble and a valuable thing. And new informatics tools offer handles to get our handle on patterns and features, and other sciences have ways to assess the meaning of those patterns and features once we get a handle on them. So I'm going to start a reading group and invite you all to join it, and keep your eye on the mailbox for that. So that is my spiel. I hope I've been connected all this time. I got zero feedback from anybody because I just had you all minimized. But I welcome your responses of any sort. Hey, there's a hand clapping. Okay, my internet didn't drop out. Good.
Yeah, thank you for this comprehensive and thought-inspiring presentation. If there are questions, do it like Natalie, turn your microphone and your camera on, and then you can begin to ask.
And of course, no offense dropping out. Well, it's not like walking out of a room. So I know it took an hour, so people, goodbye to those who've got to go.
Okay. Yeah, very intriguing presentation. A lot of different information. Now, I have a question. So when we talked about mesoscales in atmospheric sciences in particular, we always used to refer to Orlansky 1975 paper with all these different types of scales with a mesoscale alpha, beta, gamma.
Alpha, beta, and gamma, yeah, because we got 3 orders of magnitude, yeah.
Yeah, so then when we talked about mesoscale in the ocean, there is more vague definition that could be different for like equator versus higher latitudes, but it's still within similar order of magnitude. And now I wonder if you think now the quantitative definition should be retired and outlived itself, and we should talk more about the qualitative role of mesoscales. So
yeah, well, it depends, I guess, for what audience, for what purpose, for what audience. And I often wrestle with whether to engage in an attempt to wrestle familiar terms, back from meanings of them that I don't like, to reclaim familiar terms. But that's never going to reach everyone. Now there's just confusion. Or to make up some new term that's clever, a protectorate. The word protectorate totally did not catch on, by the way. That is Robert H. Laughlin and nobody else. Do you make up a new term for the thing you mean, or do you fight for a little piece of a term that other people is in other people's heads with other meanings? And that's the strategy and salesmanship of science, and I do not know the right. What's right for one author may not be for another. And in the end, this is back to that vitality. Does our field have vitality? And in a way, the vitality means somebody will patrol for meaning like that. And so when you make a claim, that will be forced through the sieve of existing terminology and forbidden from publication if it doesn't meet up. And maybe we have a low vitality field in the sense that terms are popping up and down, and new terms are easy to make, and reusing old terms is easy. Maybe we just have no culture of reconciliation in our field. So I don't know. What do you think is the good way to deal with our flabby, unvital field? Your mileage may vary.
Yeah. Okay, I think it's good to have other ways of looking at the mesoscales and not necessarily bound to any specific numbers. So.
Yeah, Fourier, right. I was trying to look for my, my section here on Fourier. Oh, I see. Yeah, Fourier. Yeah, I mean, there's a whole long history of making everything Fourier modes, so scale or wave number or whatever, and look, straight lines on a log plot, but you get the same straight line on a log plot from a piece of art. So, yeah. Okay. Anyway, thanks for asking, and let's have a let's go down to the wet lab after this and have a converse. Oh, damn it. The pandemic. But anyway, one of these days.
There's a question from Boson Zhang. Okay, thank you.
Yes, Bosong, do you want to turn your microphone on and ask your question, or?
Yeah, sure. Thank you, Roland. So, hi, Brian.
Hi.
Nice. Yeah, so I'm just curious. So, for different fields, for different phenomena, like the Madden-Julian oscillation or tropical cyclones, the mesoscale convective systems, or those kind of shallow convection. It seems to me that there is always a kind of tracking to pick those kind of isolated feature
Yeah.
or isolated system. So I'm wondering, so once we have the machine learning technique, so can we just forget about all those like mysterious tracking algorithms?
Well, yeah, and that gets back to this. Trouble is there's a non-uniqueness. So and there already is among morphometrics. What you're talking about is morphometrics, like right, blobs, deciding when two things are close enough to be one thing, and when they change from frame to frame in a movie, is that the same thing, or is that one died and another one was born, or did they split or merge, right? Identity assignment, I guess. And that makes so much sense for tropical cyclones. I mean, there's no reason to quit tracking tropical cyclones. If there's one thing that deserves the name system, or in fact, the name, Irma, it is a tropical cyclone. So there's no problem with those. But these, mesoscale convective system blob finding, I don't know. If we do new methods, those are also be non-unique. But you have to show. But then you can say they have properties. So here's the issue: when you make a morphometric traditionally, you say, the property it has is that it's easy to compute, right? Okay. It's the ratio of the perimeter to the area or something, right? It's easy to compute, so it's easy to understand what that algorithm is, but not what it means. And but when you do something a little more agnostic, machine learning-y, then it does what it does. But you can say the way you can explain it is it obeys these principles. It maximizes the difference between categories and the similarity among categories, stuff like that. So it's really at what level do you want your work to be understandable? Do you want to be able to explain exactly what algorithm you did? Then it's very objective, but what does it mean? Or do you want to be able to explain, here are the principles that we built into an architecture that created this result. And now that result is rooted in principles of information rather than, rules of an algorithm. And I kind of sometimes prefer principles of information, because some of those algorithms get super fussy, like, well, if it lasts less than 3 days, but is longer than 1,000 kilometers, then we discard it. But if we didn't discard it, then we, 5 or 10 rules, and pretty much you have no idea what it is or does anymore, even though it's very specific. So I'd rather have informatics principles behind our categorization technologies than algorithms that are laid bare, but they tinkered and fussed and fidgeted on all those rules, and you don't know why and what it really means. So
okay,
that's just a matter of taste, I guess.
I see. So after all, we cannot kind of avoid those kind of parameters in this, like either machine learning or. Yeah,
that's right. Yeah. Yeah. Do you want parameters or do you want hyperparameters, which is the name of the architectural choices in a machine learning workflow? So I don't know, but hyperparameters maybe are rooted in principles, whereas parameters are just, we threw it out if it was smaller than X. So okay. I don't know. Yeah, it's all about who it's for. Who are we writing for? Who are we talking to? What's the purpose? It's all about what's fit for purpose.
Okay. My second one is like I don't familiar with machine learning, but is it reasonable to measure the different importance of different features? That is that this feature is more important than other features.
Well, that's kind of where information is sometimes so important. Sometimes by importance, we really do mean variance, right? In our EOF modes that, categorize variance, sometimes variance is what we care about. And if you got that, boom, you don't need any new measurement. But sometimes sometimes things are important because they're informative, not because they're highly variable, right? So if you took the EOF of an orchestra, the guy swinging the stick is not especially a high variance individual, and yet there's a lot of information flow from the guy swinging the stick to the ones beating the drums. So sometimes you want to know, and that's where causality comes in. Sometimes you want to deduce causality, not just bookkeep variance. And okay. So if causality is rooted in information, then information's a better currency or metric than variance maybe. For some of these, if causality is your goal, you should be thinking about information, not squared amplitude or variance. Yeah.
Okay. Well,
that's my thought anyway.
But information is, to me, is still kind of subjective, right? It depends on from person to person. So this person is like think this is more important, but another person may say, well, this is more important. So that may disagree.
Well, but that's where I mean information now. Information is the expectation value of log probability. So if you have a probability distribution, some complicated thing, information is one number that characterizes it. So there is a way in which information can become the one scalar that characterizes, a whole complicated probability distribution. So there's information. So that was what I mean by information is, a way to turn a bunch of probabilities into one number that you can maximize or minimize or measure against some other number or whatever, right? So that's what I mean by information.
I see.
Not some qualitative, what feels informative, but within a framework, the information is a well-defined quantity. It's a thermodynamic quantity. It is entropy. And so there's a thermodynamics of information world out there. And, it's real. Yeah.
Okay, let's see what else we have. It looks as if Arthur wanted to say something.
Yes, I do. Brian, thank you for bringing the discussion about feature detection up. It's very valuable. I actually talked about it a lot in the 90s and was involved with mesoscale detection of vortices with a group from the Department of Energy. Unfortunately, the university wouldn't put the money on the table that was needed to keep up the collaboration. My experience with doing feature detection is the following. You need to define the problem first, because the best method is going to be extremely problem dependent. You're not going to find a method that I don't think, and again, I may be wrong about this, but I don't think you're going to find a method without considerable modification and changing a lot of parameters that's going to work across a broad range of problems.
Yeah.
So it's definitely, your feature detection to really optimize it has to be problem driven. Now, if you look at one simple problem, and that's just picking vortices out of, say, sea surface height fields or sea surface temperature fields in the ocean, which is a fairly simple, you would think would be a simple problem. When you compare 10 different methods and or data preparations, you get 10 different answers that vary by almost a half order of magnitude about how many vortices there are in the ocean. So this is definitely, there's a lot of work to be done. And I agree that we should start some of this type of work here at the university. I argued for this back in the 1990s, actually, that, data mining is the future of science, but, scientists are dysfunctional. Scientists are very dysfunctional. They don't like to change their viewpoints about what they learned themselves 20 years ago. So I'm glad you're bringing this conversation up, and I hope you could get something going. But I do, in some of my classes, do teach methods on feature detection, self-organizing maps, etc.
Yeah, great. I mean, I can get through my career without learning any new these things, but poor students these days are looking for jobs. What's the job market? It's full of these, up and coming new things. And as you say, they're not actually that new, but some of them. So yeah, and again, problem dependent. Yes, you use domain knowledge to extract features. So that is a problem dependent thing. And I guess what I'd say about the ambiguities is if the thing you're studying is well defined, then you don't get so much ambiguity. And so I think when you say the word how many vortices, I think the lesson of what you're talking about is that is not a well-defined question. So in a way, trying a bunch of methods and getting different answers, it sounds very frustrating, but actually that is telling you your question is not good enough yet. So sharpen your question. What do you mean by a vortex?
I think the big problem is, is the continuum of features. The fact that these features, the fact that you said that you could discretize everything, I don't think may be true for geophysical fluids. I think trying to discrete stuff is the wrong approach, because we do have a continuum. And, for example, if you look at just a small part of a Rossby wave, it looks like a vortex. And you may classify a Rossby wave as a vortex because you didn't have the image of it over space and time.
Yeah, that's right. Yeah, some of this is just, yeah, well, that comes back to what's the role for humans, right? Sometimes the job is there's a continuum. Your only discretization should be, ask Mo what's the best differential stencil to take a derivative, and then, run the computer and then work on its fields as if they're quasi-continuous. And, the whole role for human beings interpreting flow, maybe there's, I don't know. I hate to say it, but what are we good for? What is flow interpretation good for? But sometimes, sometimes there's an answer.
There is, and I think it's good for a lot of things. And as you said, I think it is going to be a more important component of the future for statistical analysis of data in our fields.
Yeah.
Thank you, Brian. Appreciate
right.
the
thanks.
provoking seminar today.
Okay, I think that's. Now there's another question, or is that a comment to someone else? From Matt.
Yeah.
That's just something internal, right? So I think we can end at this point. Thank you again, Brian, for the nice presentation.
Thank you all for coming out.
We recorded the presentation, so if you want to watch it again, you can watch it on YouTube a little later. And our next seminar will be next Wednesday by Philippe Miron of the Atmospheric Science Department. The abstract is already on the webpage. I will send the email later today. So thank you all for coming. I hope you will come again next Wednesday. Goodbye.